Recording in progress.
Oh, thank you. All right. Okay. Didn't do that before. I don't know why I do it now. I have the volume turned up. Okay, so we don't know how many times you're going to reduce the price, right? So you're going to let X, and this is kind of tricky, but let X equal the number of times you reduce the price per racer by $1. So the number of $1 reductions. That might have been easier to say that. That was kind of a mouthful I just said. The number of $1 reductions, okay? And let Y equal the money you collect. Because you can choose, right? As a business owner, it's independent. You can choose how many times you want to reduce your costs. How many times you're going to do a reduction, right? That's up to you. Good example. You see homes for sale here, right? If you actually ever in your neighborhood, does anyone have like a house for sale in the neighborhood? Like as I say, for sale sign, right? Sometimes you might see a for sale sign that's there for like several months. Something's wrong with the house. Maybe someone died in the house, or I don't know, something weird happened. Who knows? I know. Sorry, that was a little morbid. But no, I'm being serious. Like sometimes a house can't sell for some very strange reasons, right? So when you look at on Zillow, they'll see that they've dropped the price a few times, right? Ultimately, the home should sell, right? Or maybe you have some crazy owner thought their home's worth so much money and no one's going to buy until it's at the right price. So that's what we're trying to do. So you could choose that. You're the owner of a house, the owner of a racetrack, whatever. You have that choice. The money you get depends on it, right? It depends on how many times you reduce. So we're going to write like this. When we write a model, I'm going to say the money you collect is equal the number of racers times, that's a little time symbol, the cost per racer. Does that make sense? Right? How many people ride the track and the price is charged per person, right? 100 people riding, you charge $10 per person, make $1,000, right? 100 times 10, 1,000, right? This is where we're going to have to get a little more granular. The number of racers is going to be 380 plus 20x. The price per racer is going to be 35 minus x. That's a little tricky. Why is that? Because you're told the initial condition. 380 racers, $25. But what if you increase this by 20 one time? So X is 1. You do one reduction. You gain 20 riders. But you don't make as much. You make $34, right? What if you drop it 2 times? How much does it cost now? $33, right? How many more riders you get? 40. So you have 420 riders, right? Or racers. So that's how you have to set it up. Now, if you think about it, if I were to FOIL it, would I have a quadratic equation? Yeah, I would. If you're to FOIL, this is a quadratic equation. Believe it or not, it is, right? Because you can have x squared. So you could FOIL it, but if you're trying to find a maximum value, and this is already in factored form, this is where I'm going to use my reference sheet to help me out. Take a look at the reference sheet here. In factored form, let me clear the screen for a moment. Let me zoom in just a tad and mouse over. If it's factored form, how do you find the axis symmetry? You find the x-intercepts and you average it, right? And what's the vertex? Isn't that the high point? Or low point, depending on how it opens, right? But since my problem is going to be, let me undo that. Because when I FOIL it, it's going to look like this, right? Y equals negative 20x squared plus blah, blah, blah. I'm not going to FOIL it, but it's going to open down, right? Because you have the leading term being negative. If I did 20x times negative x, I'm going to have negative 20x squared. So it's going to open down. So the vertex is a high point. So what you need to do let me do this. Let me clear some stuff here really fast. Oh, what the heck's going on here? There we go. Delete, 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 erase, grab, move. Oh, goodness. Let's try that again. All right. Hold on. I'm struggling here. I'll just rewrite Y. It's not a big deal. There we go. Okay. Yeah, get rid of all this here. So what I'm going to do is I'm going to find the maximum. You need to find the vertex. And that's easy. That'll be negative 19, or that'll be 35. So you find the x-intercepts first. These are my x-intercepts. Right? Because x-intercepts is when you replace this with 0. So replace that with 0, either x has to be negative 19 or 35. So if I graph it, it looks like this. So you have 8 right in the middle. So graph will look kind of like this, right? So you have to do 8. You have to reduce the price 8 times. Does that make sense? Because then context, x represents the number of times you reduce by $1. So now find the maximum value. Well, that's easy. Just plug an 8 into your function, right? Y equals 380 plus 20 times 8 and 35 minus 8. So you drop it down to 27 bucks, you can get 160 more writers, right? If I solve for Y, I should get that much money. That's the maximum money you can make. So you've now maximized your profit, revenue, whatever. So because there's that sweet spot, right? Because what if you drop it too much? If you drop it too much, then you may not make enough money. Maybe you're not going to make a profit, right? Because that's, you got to be careful about that. So just got to be mindful of if you're in a business, how much you drop your price, right? But for the math perspective, we find the vertex. So that's a really good word problem that we did do this last year in Algebra 2. So you'll see that again because we like that problem a lot. Let's look at another one. The Tacoma Narrows Bridge in Washington State. It's probably near Seattle, I'm guessing. Has 2 towers that each rise 307 feet above the roadway and are connected by suspension cables. Each cable can be modeled by the following function. What is this between the 2 towers? Okay. All right. So when you're modeling like this, make this a coordinate plane, make that x, and make that y. Notice the tower coincides with the y-axis, right? And the place where the tower intersects the actual road is the origin, okay? That's gonna make your life so much easier. So now this equation that I'll trace in green, sorry, this curve, which I'll trace in green, goes with this equation here. That's the equation of the cable, right? So now I know what the vertex is, right? If you think about it, what's that point right there, that low point, given the equation that we see? What would I say that coordinate would be? What's the x coordinate at that point? How far along have I gone along the bridge from the south? You start here, and you go here, how far along do you go? And then how high is the cable above the car, above the road? Yeah, it's context. Good. This is context. This actually is covered quite a bit in SAT and ACT exams as well. Like, can you see the context of it, right? So yeah. So now if I think about it, if this is where you start, right? If that's the origin, by the time you're to the vertex, you travel 1,400 feet. So what's the distance between the two towers? So how far have you traveled between the two towers? If that's 1,400. You go from here to 1,400. How far is it between the two towers? 1,900. Okay, that's great. 1,900. Yeah, that's it. You don't have to do any math, really. You just have to just think about it, right? I mean, yes, you do some math, but you don't have to do any crazy math, right? You just have to just really just think about it. So the distance between the two towers is 2,900 feet. That's all. It's that simple. So that's using a model. But what you have to do is you have to superimpose this image onto a coordinate plane, right? Or put the coordinate plane on it and make sense of it, right? So it's not that hard once you get the hang of it. So, or for example, what if you want to know how high the tower is? Okay. Has anyone been to, I know it's kind of a crazy question. Has anyone been to Australia? Sydney? Okay. So, well, I was there many years ago, but you guys have the Sydney Harbor and then you have the bridge. Some people actually could walk on top of the bridge. I'm not sure if you know that. It's kind of crazy. I didn't do that. I was too scared to do that. But you know, if you want to know how high you are, how high you are on top of the bridge, how would I figure out how high this tower? What would I do? What would I plug in for x? Remember, this is the y-axis, right? What's x value here on the y-axis? So you plug in 0, and I'll tell you how high you are above the bridge. Yeah. So if you have the equation, I mean, of course, if you do this crazy thing, you want to walk on top of a bridge, they would just tell you if you're a tourist. But if you have the equation, you can figure it out that way too. So anyway, let's do a couple more. Let's see here. Let's look at number 3. Okay, the path of a place kick football can be modeled by the following equation, where x is the horizontal distance in yards and y is in height in yards. Because football, you have a 100-yard field, right? That's how it's done. So let me draw a coordinate plane. Let's find the x-intercepts of this. What are my x-intercepts here for that equation? Where's 6 and what's the other one? It's a little tricky. You have negative 0.026x times x minus 46. So either x has to be 0 or x has to be 46. Because think about it, the ball's on the ground right now, right? And you kick the football and it lands right here. So that's the trajectory of the football. If you know, you guys watch football games all the time, right? Like that's what happens. You know, they line up for a field goal, kick it, and then goes down, right? So how far is the football kicked? Well, it's kicked 46 yards. Okay. Actually, be a more fun question. Would it cross the would cross the crossbar or whatever you call it? I should know that. I love football, but would it be a good field goal? Like would it actually, or would it hit the crossbar or whatever? Right? We're not going to do that because that's kind of a fun question. But sometimes you need to know how high it goes, so we'll actually clear that height when it reaches that point, right? But we're not going to concern ourselves about that right now. But what's the maximum height? We could do that. Where's the vertex, guys? At what x value? 23. Halfway between. Yep. So you just plug it in. And whatever that is, that tells you how high the football is above the ground at its highest point. Let's see here. So it goes about 13.754 yards above the ground, which is about 40 feet. So sounds about right. So yeah, that's what's happening with that one. And here's one that involves I think we kind of done this one already. Yeah, you have a rectangular park and you want to change the area, you want to expand it, run an equation, and then what are the new dimensions of the platform? So, okay. So we've done this kind of problem before. So that's 10. And 12. We want to add to each side of the platform. Okay. So it's going to be 2x plus 10, 2x plus 12. And here's the thing. You want to triple the area. So it's going to be 3 times 120. Because think about the area right now is 120. But you want to triple it, so you want to make it 360. So you said equal 360. And if you work it out, you should get 4x squared plus 20x plus 24x plus 120 equals 360. Factor out the 4. Plus 15 minus 4, I think. But you're not going to have negative dimension. That's weird. So you're going to increase by 4. So now it becomes 18. So if you increase by 4 on each side, it becomes 18 by 20. Now you have 360 feet, square feet, whereas 4 is 120. So that's a very classic quadratic equation work problem. We have a diagram, right? I know you guys have a rectangle. You said you're adding x each side. You do that. Actually, the wording was pretty good. Add the same this x each side of the platform, and then realize oh, that's 2x plus 20. Sorry, 2x plus 10, 2x plus 12. You multiply those together. You want triple area. The area is 120, so now it's got to be 360. And then you just it's all math at this point. Right? It's all output. Just FOIL, bring things one side, factor, solve, and you have your answer. So, so you guys have this now as a guide. Actually, it's a really nice solution. Let me save this as a PDF. There we go. Okay, just so we close the loop, I'd like to do more of these notes here. And M&A, let me get you guys started right now. I'll put you in the study hall. The rest of you guys will be back in a sec. You want to do it too?
Yeah.
Yeah, I'm getting that here. Yeah, I opened up from 229 right across all three down. It's just right across all. It's results in 3. All right. Okay. Let's talk about this one here. You're asked to graph this equation. So I haven't taught you guys how to graph this yet. I did a vertex form. I did a intercept form. This is the formula to find the x-coordinate of the vertex if the equation is given to you in standard form. The reason why this works, Again, you don't have to write this down, but you guys know this, right? Negative b plus or minus root b squared minus 4ac over 2a, right? What does that truly represent? The x-intercepts, right? Using quad form. If you were to average it, if you say negative b plus that radical over 2a plus negative b minus that radical all over 2a, and the whole thing is over 2, you're averaging it, what's going to happen is that the radical is going to go away. You're going to have negative 2b over 2a, the whole thing is over 2. And those twos are going to cancel, leaving with negative b over 2a as a result, if you do your fractions correctly. So that's where that comes from. It's just the average of the x-intercepts. We're just going to apply the formula, which is negative 2 over 2 times 1, because your b is 2, your a is 1, right? Because you don't see a number in front of x, but you assume it's 1. So you get negative 1. Y equals negative 1 squared plus 2 times negative 1 minus 3. 1 minus 2 minus 3, you get negative 4. Then let's make a little table. Plug in a couple of values for x, one on each side of the vertex, 0 and negative 2. You should get negative 3 in each case, I think. Yeah. There you go. Pretty simple, right? This one here, same thing. I'm going to do negative b over 2a. Negative 4 over 2 times 1. I get negative 2. Which should be negative 9, I think. Or make a little table. Now, this is tricky. I haven't talked about inequalities yet. But you make the curve dashed because it's not included. And you shade above. Because greater. Now, if there's an equal sign greater than or equal to, then make it solid. And you shade above, so it looks like this. If you're a test a point like 0, 0, it would work. 0 is greater than negative 5. 0, 0 is included in the shaded region. So that's what's happening at that one. Okay, so yeah, I know I didn't do linear inequalities. It works the same way. If you have a linear inequality, you graph the line. If it's not equal, you do dash. It's equal, pretty close, you do solid. You shade above or below. Once you have y isolated, it's greater shade above, less shade below. Same thing for the inequalities, or quadratic inequalities. You always shade above your boundary if it's y is greater than the rest of the expression. We shade below the boundary if y is less than. So that's how that one works. Sketch the 4 scenarios. Let's just skip that. You know what? Let's skip the rest. I didn't really intend to go over quadratic inequalities. Now I know what they're asking. I don't care for that. So yeah, so that kind of no more new stuff I want to do. I just want to do a review. So the way we're going to review today, we'll look back at some old homework problems if we have a chance to do that. I mean, 11 and 12 look pretty good, but maybe we don't have to do that today. 11 looks pretty good too, actually. Let's do 11 really quickly on the homework. But we're going to play this Jeopardy game where we'll talk about equations and graphs. And it's kind of pretty basic stuff. It kind of goes back to last week. I'll see if I can find another game if we finish this one and I still have some time to spare. I also do like a Mr. E category. So this is actually, I'll let you guys use your cell phones for this. I know we're gonna be a cell phone free school in 2 weeks, but I'll let you use your cell phones if you want to do a little like cyber stalking or sleuthing of like looking stuff up about me. It's kind of fun. We this is it's a fun game to play. I get to know who are the creepos in my class. So anyway, it was really good at searching stuff on the internet. So anyway, we'll do that after a break. But before we do a break, let's just talk about one other word problem here. So like the Golden Gate Bridge. Okay, so this is a bridge. Actually, I was in San Francisco yesterday meeting a friend. Well, it's actually close to the Bay Bridge, not the Golden Gate Bridge, but you know, let's say one of the cables is modeled this way, right? And how far above the road will the lowest point of the cable be? And the Golden Gate Bridge, you know, you can actually walk on the bridge. It's kind of a fun thing to do, right? Some people, a lot of tourists do that sometimes. So negative b over 2a is find the x coordinate of the vertex. And let's say this equation models one of the cables on the Golden Gate Bridge between two consecutive towers. How high will the cable be above your head when you're at the lowest point? When you walk on the bridge and you see the lowest point of the cable, how high is it above your head, right? So if you do negative of negative 7/15 over 2 times 1 over 9,000, work that out. I'm gonna use a calculator for that one. Because the cable, you know, here's the Golden Gate Bridge, right? That's what we want to find, right? What is that x value between two towers? Let's see, 7/15 divided by 2 over 9,000. Ooh, comes out really nice. Comes out to 2,100. But then you have to plug that into the equation. So 2,100 feet, that's roughly half a mile, right? A little less than half a mile. So you walk about half a mile. The cable's gonna be below. You're gonna be below the lowest part of the cable. So your square divided by 9,000 minus 7/15 times 2,100 plus 500. Actually comes out really nice too. 10 feet. I wonder if that's really true. But yeah, I guess the lowest point of cable would be 10 feet above your head. Actually, I'm kind of curious. Let's look that up. Lowest points. In the Golden Bridge. Oh, okay. 6 feet above. Okay, so this equation's off a little bit. Okay. All right. Yeah. Oh, okay. Yeah, so that's one big cable, right? So yeah, it kind of makes sense. And actually, what if that's really true? Okay. Anyway, but yeah, kind of neat. So, okay, so my equation, this equation was off a little bit, but it's all good. All right, so let's take a break. Let's come back around 10:10, and then we'll play Jeopardy after that.